Hi guys, good morning. Today we are going to discuss logic gates. So these logic gates are basic building blocks of digital systems. So logic gates are electronic circuits because they are made up of a number of electronic devices and components. They are constructed widely. They are usually embedded in large scale integrated circuits, very large scale integrated circuits along with large number of other electronic devices, and it is not easily accessible and identifiable. So each gate is a dedicated specific logic operation to identify. So logic gates have input and output of logic gates can occur only two levels, that is high and low. So it also can be termed as true or false. Simply we can represent 1 and 0. 1 and 0. So we have different types of logic gates: NOT, AND, OR, NAND, NOR, XOR, XNOR, and buffer gates. So NOT, AND, OR, these three gates coming under basic logic gates. These three comes under basic logic gates. NAND and NOR. These two comes under universal gates. Why it is so called universal gates? Because by using these two NOR and NAND logic gates, we can implement any of the logic gate. We can implement any of logic gates. So first of all, we can discuss basic logic gates, that is AND, or NOT, and or NOT. Coming to NOT gate, it is also called as inverter. It is also called as inverter. So it has only one input and one output. The logic diagram of the NOT gate is here we can represent, and the Boolean expression of the logic diagram is input is A and output is X. So X equal to A bar. X equal to A bar. A bar. So this is the truth table of NOT gate. A is the input, X is the output. So it's specify the complementary operation. Specify the complementary operation. X equal to A bar. If we input A is 0, the output X equal to A bar means X equal to 1. If input A is 1, X equal to A bar means X equal to 0. Equal to 0. So coming to another gate is AND gate. Specify the multiplication operation. Specify the multiplication operation. It has two inputs and one output. So observe the here I can represent logic diagram of the AND gate and also represent the Boolean expression X equal to A into B. So X is the output and A and B are the inputs, and A into B specify the multiplication operation. And this is the truth table of AND gate. Table of AND gate. If both coming to truth table of AND gate, the both inputs are high, the output is high. So specify the X equal to A into B, A equal to 1, B equal to 1, 1 into 1, 1. If any one of the input is 0 or both the inputs are 0, then output is 0. 0 into 1 or 1 into 0 or 0 into 0. Specify the output is 0. And coming to next gate is OR gate. OR gate. OR gate specifies the operation of sum operation. Sum operation. So this is the logic diagram of the OR gate. Logic diagram of OR gate, and this specifies the truth table of the OR gate. This is the Boolean expression. It has two inputs, the represented in A and B. The output represented in X. So it specifies the sum operation. So X equal to A plus B. A plus. We can design truth table. If A equal to 0, B equal to 0, 0 plus 0, output is 0. If A equal to 0, B equal to 1, output is 0 plus 1, 1. If A equal to 1, B equal to 0, output is 1 plus 0 is equal to 1. If A equal to 1, B equal to 1, 1 plus 1, X equal to 1. So specify the operation. If both the inputs are 0, output is 0. If any one of the input is high or any one of both inputs are high, then output is 1. So these three basic logic gates are completed and or not. So NOT gate specify the complementary operation, AND gate specify the multiplication operation, and OR gate specify the sum operation. OR gate specifies the sum operation. And coming to next gates, universal gates. Universal gates. These are NAND and NOR gates. NAND and NOR gates. So why so it is called as universal gates? So we can implement any of the logic gates using NAND and NOR gates. NAND and NOR gates. That's why it is called as universal logic gates. So coming to NAND gate. Coming to NAND gate, this is the logic diagram of the NAND gate and truth table of the NAND gate, and this is the Boolean operation. So NAND gate operation is exactly complementary of the AND gate operation. Exactly complementary of the AND gate operation. So this is constructed using AND gate followed by NOT gate. This is constructed using AND gate followed by NOT gate. AND gate with bubble AND gate. So these two A and B are the inputs and X is the output. X equal to A into B. Here it is constructed bubble AND gate. So A into B whole bar. The Boolean expression is A into B whole bar. So coming to truth table, it shows exactly complementary to the AND gate. Exactly complementary to the AND gate. What is the truth table of the AND gate? If any the two inputs are high, the output is high. If any one of the input is low, the output is low. So coming to NAND gate, the two inputs are high, the output is low. The any one of the input is low or both the inputs is low, the output is high. So you can observe it exactly complementary to the AND gate. Okay. Coming to some other gate, that is NOR gate. NOR gate. So this is the logic diagram of the NOR gate, and this is Boolean expression and truth table. So NOR gate specifies the bubble OR gate. Bubble OR gate. AND gate, NAND gate specifies the bubble AND gate, and OR gate specifies the bubble OR gate. Means the complementary of OR functionality. Complementary of OR functionality. We can also build this NOR gate, OR gate followed by NOT gate. Followed by NOT gate. It has two inputs and X is output. So X equal to A plus B whole bar. X equal to A plus B whole bar. So coming to the truth table, it's exactly complementary to the OR gate. Exactly complementary to the OR gate. What is the Truth table of OR gate, if any one of the input is high, output is high. But here we observe the any one of the input is high, the output is low. Any one of the input is high, the output is low. Both the input A0, B0, A plus 0 plus 0, 0, 0, 1, 1. If A1, B0, 1 plus 0, 1, 1, 0. 0 plus 1, 1, 1 bar 0. 1 plus 1, 1, 1 bar 0. This is the NOR gate operation. Coming to next one is XOR gate. So you can also call it as exclusive OR gate. So this is the Boolean expression of exclusive OR gate, and this is the logic diagram of XOR gate, and this is truth table. So the output of the XOR gate is modulo sum of its two inputs. Modulo sum of its two inputs. A and B are the input, X is the output. So we can observe XOR gate. Any one of the input is high, then output we get high. Any one of the input is high, then output we get high. If the both inputs are same, are 0 or 1, then we get 0 as output. 0 as output. So it is also called as inequality detector. Inequality detector. Then coming to next one, exclusive OR gate. Exclusive OR gate. The logic symbol of the exclusive OR gate is exactly complement to the XOR gate. It is exactly complement to the XOR gate. So by observing truth table, we can know that from XOR gate and XNOR gate. XOR gate, the any one of the input is high, the output is high. Coming to XNOR, any one of the input is high, the output is 0. The output is 0. The both inputs are 0, the output is high. The both inputs are high, the output is high. So this is exactly complement to the XOR gate. And coming to buffer. Buffer, it acts as a same output to the input. But input we are given, that output we get. If input is 0, output we get 0. If input is 1, output is 1. Coming to next one is combinational logic circuits. So guys, this we can discuss tomorrow.